All right, excellent. Thank you everyone for coming to this webinar. My name is Ravikumar, and I'm an assistant professor at Harrisburg University, where I run the Sustainable Energy Development Lab. Again, thank you for agreeing to be part of the technical working group on the Path to Equivalence project. The Path to Equivalence project, for those of you who are new to this webinar and new to this project, is a collaboration between Colorado State University, Harrisburg University, and UT Austin to develop a framework that will help evaluate new technology systematically for use in methane leak detection and repair programs. So the way the Path to Equivalence project started is through a series of stakeholder workshops in Canada and the United States. These workshops invited members from the industry, from regulatory agencies, as well as academic scientists to understand the scope of new technologies in methane emissions detection and methane mitigation in general. These workshops were held through the course of 2019 and late 2018. And what came out of this is a framework called the Path to Equivalence project. This framework, in short, consisted of 3 different steps to evaluate new technologies. The step 1 is controlled release testing of new methods at a test facility like METEC in Fort Collins, Colorado. The second step consisted of modeling these technologies in a simulation framework to understand whether it is equivalent to existing methane mitigation programs. And the third step are field trials at producing oil and gas facilities to understand the real world performance of many of these alternative technologies and methods. This webinar and this part of the project in the Path to Equivalence framework is focused on step 2, which is the modeling. What we are going to be discussing in this webinar is feast. Feast stands for the Fugitive Emissions Abatement Simulation Tool. That was initially developed at Stanford University, where I was a postdoc, and Chandler Kemp, who will be leading the seminar, was a master's student. Feast was initially developed to be able to compare different technologies on the same platform. So you had a lot of new technology development with methane sensing instruments on platforms such as drones, planes, trucks, and even continuous monitoring instruments. And we wanted a tool to sort of understand how these different technologies would perform on a methane, on an oil and gas site, without actually having to go and test out each one of them at these sites. And so we developed this framework that sort of hypothetically put all these technologies to work at an oil and gas facility and looked at what fraction of methane emissions can each technology detect, and therefore what kind of mitigation would we get if we replaced existing systems with some of these newer technologies. So right now we're going to be focusing on this model, Feast. Many of you have already heard about this model, but what we're going to do now is I'm going to turn it over to Chandler. He is a research associate at Harrisburg University, and he has been leading the development of Feast since about 2016, when we published the first paper on this model. He can walk you through the different parts of Feast, but we'll start with a general introduction to what is Feast and what type of results we can get from using this model. We'll then move on to some of the technical and the coding details of this modeling, where we'll get feedback from all of you through different technical working group sessions. All right, so how is this webinar going to work? We have allotted about 2 hours for this webinar, but the actual Feast model portion is only about an hour. And we have set aside about an hour for questions and any troubleshooting any of you might have with the code or the model or other questions. The way it's going to work is, because we have about 20 participants on the webinar, it'll be difficult if everyone had a question and just unmuted their microphone. So what we'll do is I'm going to mute everybody at the start except Chandler. and he's cognizant of that fact, and he will pause every 10 minutes or so for people to ask questions. In the meantime, while Chandler is presenting his slides, if you have any pressing question, there's a chat function on the Zoom tool. If you click on chat, you'll be able to see a dialog box open, and you can type your question there that will go to everyone. What I'll do is I'll be monitoring the chat, and whenever Chandler pauses, we'll go through those questions and he can answer them for you. Before I turn it over to Chandler, I want to let everyone know that I'm recording this webinar. So the webinar and the slides, everything will be made available online if you want to go over it one more time after this webinar is ended. Before I turn it over to Chandler, any questions from anyone in attendance? So you're muted by default. So if you want to speak, just unmute yourself and ask your question. All right, excellent. All right, that's it from me. And Chandler, over to you, and please get started.
Great, thanks, Arvind. So I'm going to go ahead and start sharing my screen here. If anybody can't see it, please do post a message in the group chat, and Arvind can let me know, and we can pause to make sure everybody's able to see my presentation here.
Yeah, just give it 30 seconds or so to make sure everybody sees the slides.
Great.
Yeah, again, please use the chat function if you cannot see something or if you cannot hear Chandler, and we'll try to troubleshoot it for you. I'm also going to mute myself so there's no interference from my end.
All right, so like Arvind said, I'm presenting the Fugitive Emissions Abatement Simulation Toolkit, or FEAST. And specifically, my goal for this presentation is to enable all of you to install the software on your own machine, learn to run simulations using the software, and assess results. So I'm really hoping that by the end of this webinar, you'll be empowered to run FEAST on your own. So I've got an outline of where I'm headed here. First, I'm going to give a presentation of the model architecture. So this will include a few slides about how the computer program works and what we're trying to do with it. And I'll move on to a Jupyter Notebook tutorial. So this is available online, and I'll walk through how to access it and how to run a few commands in that tutorial. And you're welcome to, after the webinar is over, you'll be able to go on and log on, make your own account, and run FEAST there without doing any installation or worrying about the environment that you're working in at all. Once that's complete, I'm going to give an overview of an example run script. So that's a method for running a highly customized simulation within the software. And finally, I'll go over the installation procedure and ask for questions.
Chandler, Peter doesn't seem to be seeing your slides. He says he's just seeing a black screen. Is anyone else also having problems with seeing Chandler's slides?
Oh, we've got it now. Don't worry.
All right, great. Thanks, Peter. Carry on.
Okay. All right, so for those of you that don't know, FEAST simulates the impact of leak detection and repair programs on emissions from natural gas fields. And so the software is intended for a variety of applications, including estimating emissions under various leak detection and repair programs and gas field assumptions, directing leak detection research through sound modeling of the impact of technology improvements, informing investment decisions based on the cost of deploying leak detection and repair programs and the value of gas saved. And finally, what we're really focusing on during this project is comparing the mitigation potential of LDAR programs in order to design effective emission policy. In order to do that, FEAST relies on a Markov process. So what that means is it iterates across a series of time steps. And at every time step, each component that's simulated in the gas field has some probability of transitioning from a robust non-emitting state to an emitting state, and vice versa. So there's some chance it's going to be repaired, and there's some chance that it's going to break at every time step. And so we iterate throughout time to generate a time series of emissions. In order to do that, we need a variety of types of input data. The first is we need to define the gas field that we're working in. So parameters that characterize a gas field are things like the components that are present there, the number of wells per well pad, maybe the distance between well pads, and how long it takes to get from one to the next. We also need to characterize detection methods. So detection method properties include things like the probability of detecting emissions of different sizes, and maybe the conditions or the conditions that the technology can be applied under. Finally, we need to know not only about the detection technology, but also we also need to know about the program that surrounds and supports that technology. So these include things like the survey frequency, the costs of conducting a survey, and if there's any time delay between when an emission is detected and when it's actually repaired, if it's a leak. So combining all of these things, we can generate a time series of emissions. And that's the basic result that we're looking at in feast. So I'm going to zoom in on that time series now and highlight a few more details of what feast can do. So here I have a time series of emissions. It's years along the x-axis and emissions in kilograms per day per well on the y-axis. And you can see a few different curves there. The blue curve across the top is the total emissions without any explicit leak detection and repair program. So as you can see, the emissions vary stochastically throughout the simulation, but they're approximately constant. In addition, the orange curve is showing the total emissions if a optical gas imaging camera-based leak detection survey program is applied. And so what you can see is there's a periodic variation in the emissions. Each time there's a survey, the emissions decline quite rapidly, and then they slowly build back up over time until the next survey. So here in this simulation, there's a survey happening about twice a year. Finally, the green solid area across the bottom shows vents. So these are emissions from the gas field that cannot be repaired. They're part of the design of the operations. So these vents, they're the same regardless of whether you're applying an optical gas imaging camera or no leak detection and repair program or any leak detection program. And what we're showing here is that with the OGI camera, whenever there's a survey, almost all of the leaks that can be repaired are repaired. I want to zoom in even further just on the beginning of the simulation to highlight a couple more details. So this is showing the first 30 days of that same simulation. You can see the same green area, the same blue and orange curves, but you can also see some high time resolution events here. So these high intensity short duration events are representing unloadings. So I want to highlight here that with the feast does allow for simulating short duration intermittent events. Also, I want to point out that feast does accommodate finite survey times. So here the emissions are declining over the course of about 30 days. And that's because of the settings that we've imposed during the simulation, which determine how quickly the gas field can be surveyed using an OGI camera. So that's an overview of the basic process within feast, how we represent gas fields. And next I'm going to move on to representing leak detection and repair programs. Before I do that, I want to pause here to see if there's any questions.
Yeah, if you have any questions when Chandler is paused, just unmute yourself and ask a question.
Hi, this is Arstina from Chevron.
Hi, go ahead.
So I just wanted to confirm my understanding. So the frequency of the survey with OGI can also be set up like monthly, once every 2 months, things like that?
Yeah, exactly. Yep. And you could even define multiple parameters at the same time and compare the impact of these different survey frequencies.
Great, thank you.
I'll give just a couple more seconds if anybody wants to chime in. Okay, so when we go ahead and simulate a detection technology, feast relies on a probability of detection curve. So I'm showing an example of that here. I have the emission rate in kilograms per day along the x-axis and the detection probability on the y-axis. The 5 dots you see on the curve are measured data points. So this is from a 2018 study where Arvind and a few others went to METEC and measured the allowed several different sizes of emissions that were known and determined what fraction of those emissions were detected by a trained OGI operator. Of course, we know that the probability of detection depends on many parameters in addition to the emission rate. You know, for example, the experience of the OGI camera operator and weather conditions are two important variables. But here in this realization of feast, we've simplified that complex probability of detection surface into this one-dimensional curve. And that's for 2 reasons. The first is to make the model a little bit more simple and easier to interpret, but also because of the data that's available. You know, we have data that can support these one-dimensional curves, but we would need more data in order to support a more complex surface. So in addition to the OGI camera, we have similar data for other types of technologies. This is showing the probability of detection curve for a plane-based technology. And I want to highlight here that for a plane-based technology, it may only identify the site where emissions are occurring, but not the specific component that's leaking or venting. So in order to actually go back and repair those leaks, a secondary survey is required, typically with an OGI camera. And so that's another type of detection system that feast does support. We call it a tiered detection system, where a preliminary survey is done by a technology that can only identify site level emissions, and then a secondary survey follows along that identifies the specific components that are emitting. Okay, so now that we have an idea of how we model a gas field and how we model leak detection and repair programs, we can combine those two to have a deeper understanding of what that time series is showing that I mentioned earlier in the presentation. So here I'm showing results from a single realization of a scenario that had 2 different technologies, an OGI camera and a plane-based detection system. So again, you can see that the emissions are highly variable, random, but there's also a general trend here. In general, the OGI camera results in fewer emissions than the plane, and the plane in turn results in fewer emissions than the no leak detection and repair scenario. But in order to really understand how significant that trend is, we can't just look at one realization. We need to run a Monte Carlo simulation, generate many realizations of the same scenario, and look at the range of results that occur. So here I've added another realization into the time series. So you can see there's a little bit more overlap here. And then on the box plot on the right, I'm showing the range of results that we see across a high number, or in this case, actually only 30 realizations of the same scenario. So you can see that there is some overlap between the different leak detection and repair programs, but the median emissions are also different. So finally, feast also allows for cost estimates. So some of the parameters that you can define in feast include the dollars per hour for operating an OGI camera, or the dollars per site for a site-based leak detection program, as well as and so when the simulation runs, those parameters allow the software to calculate an estimated cost. And if we combine that cost with the difference in emissions throughout the simulation between a leak detection and repair program and a scenario with no leak detection and repair, we can estimate a mitigation cost. So that's what I'm showing on the right. I have the OGI scenario and the plane-based scenario on the x-axis, and the mitigation cost in dollars per metric ton CO2 equivalent on the y-axis. So of course, I've included an assumption there about the global warming potential of methane. In this case, I've set it to 34. And I also want to highlight here that I've not included the value of the gas that's saved. And so if we include that, that value, the additional revenue that might be possible, then we would get a different result here. Okay, so finally, this is the last slide before I move on to the Jupyter tutorial. I want to highlight how customizable Feast is. So a few examples of things that you can customize in Feast are the component types that are included in the simulation. So you can define as many different component types as you want and enter them all into a gas field that will then be run through the simulation. Those components can include things that vent, as well as things that leak, as well as intermittent emissions. So a few examples are you could represent an open-ended line, you could represent tanks, you can represent unloadings, and all these different types of components are, in this case, modeled by the frequency at which emissions occur and the distribution of sizes of those emissions. So to define the distribution of sizes, I've listed those parameters as items that can be edited for each component on the slide there. In addition to these component types, we can also change the way that they're combined into sites, and we can change properties that relate the sites to each other within a gas field. Similarly, we can customize leak detection and repair programs. There's two basic types that are supported by Feast: mobile surveys and tier detection programs. I've mentioned those before. Examples are an OGI camera and a plane-based hybrid leak detection and repair method. And the parameters that we can set for these leak detection and repair programs are things like their sensitivity, their cost, and their frequency of deployment. All right, so that's the end of my summary of what we're trying to do with Feast, the types of questions we can ask, and the types of parameters that we can control. So before I move on to the Jupyter Notebook, this is another opportunity to ask any questions.
One thing I want to note here is that Feast or any model is only as good as the input data that's presented. Right now, when we hand over Feast to you through the GitHub platform, we'll have default data that's available, but we're also working closely with UT Austin and folks at Colorado State University to sort of integrate Feast with a more detailed emissions model. So if you have detailed emissions data at the component level at your disposal, you could always use that data and see how Feast performs using those data inputs. One of the things that we have seen in the real world, as well as in modeling, is that the effectiveness of your leak detection often depends on your leak size distribution and the type of emissions that you have on your site. So it's always good to have additional data into these models. And if you do have some data and if you want to incorporate them, we can definitely help you bring that in a format that would be as a good input to Feast. But I'm going to stop here and let you ask questions to Chandler.
Hey, Chandler, this is James Van Horn with SLR. What's the purpose of putting in like unloading events that are like planned maintenance events? I mean, I wouldn't see those events as being necessarily reduced, emissions being reduced by a leak detection program.
Yeah, great question. So the unloading events are included for a couple of reasons. One is that they can increase the cost of some types of survey programs. So for example, you might imagine if you have a plane flying over, there's an unloading event, it's going to flag that site as high emitting, which incurs an additional cost of then sending out the OGI camera crew to see if there's a leak. And when they actually get there, they determine, oh, actually there was only an unloading event and there's nothing we can do about it. So it doesn't affect the LDAR program doesn't affect the emissions from the unloading event, but the unloading event does affect the cost of the leak detection and repair program.
Gotcha. Thank you.
This is Clay Bell at CSU. To follow up on that question, one of the other things that we kind of anticipate is if you are doing an analysis on something like a continuous monitoring system, the sites have venting sources, right? And there's some stochastic variability in when and where those sources occur in the site. And to a continuous monitor that's, say, a set of point sensors along the fence line, if they're measuring concentrations, kind of discerning between a leak and a vent would be a challenge, and somehow maybe need to be modeled in there. So kind of having a whole or assessment of total emissions from the site, I think, would be necessary to evaluate that type of solution.
Thanks, Clay. Right now, I think one of them asked a question in the chat. Feast is right now set up to simulate upstream onshore production facilities. It can also include midstream facilities such as compressor stations, but the version that you're going to be using does not include any pipelines or distribution systems within the framework. All right, go ahead, Chandler.
All right, great. Yeah, thanks for that question. So now I'm going to move on to show you some of the resources that are available to help you get used to using Feast online. The first is the GitHub account. So the link is available on the slide here. You don't necessarily need to follow it right now. You can type it in, after the webinar on your own time and look through it. But I will go to that link myself, and you can watch through the screen share what's available there. So this is the GitHub account page. Arvin, can you confirm that you can see the GitHub page in the screen share? Great.
I can. Just give it like 10 seconds so that it takes a while for it to refresh on other people's screens.
Okay. So while it's loading, I can explain a little bit of what's available. If you haven't looked at a GitHub repository before, the first thing that shows up is the list of all the files and directories that are included in the software package. So that you can see that in the screen share. And if we click on any one of these files, it will bring it up and we'll be able to look at it. So
increase the font size, just zoom into the screen.
Yeah.
More visible. Yes, thanks.
Great. So here you can see the list of files. In this parent directory, many of these files include meta information, things like the license, there's a README file, there's a brief glossary. And if we click on the directory at the top there, Feast, we can see some more of the code that we actually use to run the software. And if we want to look at one of those code files directly, we can click on it, and you can view it right on your web browser there. But for now, you can do that on your own time. But what I want to highlight right now is the README file. And then in that case, you don't even have to click on the link. You can just scroll down, and the README file is available here. It gives an introduction to what Feast does, a little history of the software, and it also includes a map of all the files that are in the software. So if you're trying to find a file, this is a good resource to look to. And below this, there's also a description of each of those files. So again, you can look through that on your own time. I won't go through it now, but I do want to point out this link to a tutorial. So this is where you can access a Jupyter notebook. And the power of this is that the software is already installed on the server, and the necessary packages are already installed. So if you just want to get an intuition for how Feast works without bothering with an installation, this is a good way to do that. So if you click that link, it will bring you to the Jupyter Notebook page. I've already logged in my case, so it brings me to this page immediately. But if you're not logged in, it'll bring up a page that looks like this. And you can enter any username and password you want. As soon as you do that, it'll create an account with that username and password. And within that account, you can do whatever you want. You don't have to worry about breaking anything. It's a separate realization of the software and the environment. So you can enter whatever commands you want and change any files you want, and it won't affect anybody else. The only caveat I would say is that we won't save your work indefinitely. So you shouldn't do work there that you really want to save for a long time. But if you do log in and out a few times during the course of the day, you should be able to access the work that you've done. And one other thing I want to note is the first time you do this, it will come up with a screen that asks if you want to spawn a new server, and you should go ahead and click yes. And then it will take a minute or so to create that new account server for you. So once you've logged in, it will bring you to this screen. And the first thing you'll see is this feast_pt directory that includes all of the files that come with Feast. And if you click on that, there's one called feasttutorial.ipynb. And that's the notebook itself. And so if you go ahead and click on that, it will bring up a Jupyter notebook with commands that you can run. If you haven't worked with a Jupyter notebook before, it's a way to combine textual information, computer programming commands, and figures all in the same platform. So you can see at the top, there's a block of text, and then below that, the block that's in a little bit different background color, that includes commands. And if you want to run those commands, you simply press Shift-Enter, and a little asterisk appears while it's running. And once the command's completed, then it shows a number instead of that asterisk. So this first code cell, so this Jupyter notebook shows exactly how you can run Feast with very little preliminary work. So the first thing you have to do is import a few packages. And so you can see in this line here, I'm importing the Feast package. And I'm importing a few other packages that I'll use just to manipulate files and look at results. But they're actually not, you don't necessarily need to include those packages just to run Feast.
Chandler, can you zoom in?
Oh yes, sorry, thank you.
Maybe it's just my screen, but yeah.
So I'll go ahead and pause here just for a second to see if there's any questions about Jupyter notebooks or how we can run commands.
What was the shortcut to run a section or a block of code again?
It's Shift-Enter. Okay, so I'll go ahead and move on. So now if you want to run a simulation, the simplest way is with this field simulation command. And you can see I've entered no input arguments to that command, which means if, when we run that command, the software will look to see if there are any input arguments. And if there are any, it will use them. But if there are not input arguments, it will use default settings. And you can mix and match. So you can define a few parameters that you want to change, and it will use default settings for everything else. So in this case, with 0 input commands, it runs with all the default settings. So it's not a particularly meaningful simulation, but it is useful just to see how the program works. So if I press Shift-Enter on that, it runs the simulation. It gives you an update every time a simulation is 10% complete. And it's now saved that result to a results file. If we want to look at that result, I've included a couple of plotting functions by default that take care of the overhead of loading a results file, accessing the parameters that you want to see, and then plotting them in a way that's intuitive. So one of these plotting functions is called time series. So you can see I'm importing it here. And then I specify a path to the results file. I happen to know, what that path is by default. And so I run the time series command. It takes one parameter, which is the path to the results file. And then optionally, you can also set the line width. I've set it here to be a little bit fatter, so it's easier to see in the presentation. So again, if we press Shift Enter here, it's going to update this plot. So what's showing right now is a realization of the same scenario that I just ran, the default scenario. So the new result should be similar in that we should see a similar difference between the no leak detection and repair program and what by default is called a tech detect program. However, the details, like where the peaks are exactly and how high those peaks are, we should expect to be different. So I press Shift Enter, it takes a second to load the file, and there's the result. So again, you can see it's a bit different, but the general trends are the same. So hopefully that gives you an idea of the really basic way to run the software. But then if you want to, the immediate question is how do we do something useful with it? How do we customize the simulation to represent a specific gas field that we're interested in, or a real leak detection and repair program? So I'm going to go through that now. If on your own time, if you're looking through this Jupyter notebook, there's a series of commands that allows you to do that. But I'm going to switch back to PowerPoint for now to give a few, so that I can display some images that help show what these different commands are representing. So when I want to run a highly customized simulation using Feast, sorry, there we go. I write a run script. So that pulls out all the customization commands into their own, into a separate file. And then that file can be run over and over or subtly changed if we want to make adjustments. So these files can be pretty long because we can, I sometimes end up defining hundreds of different parameters within Feast. But I'm going to go through this bit by bit to explain how it works. So to understand it, I want you to keep in mind this tree model of how data entry is structured within Feast. So at the bottom level, we have components. I list a few examples of the parameters we can set for them here. But we can define many different types of components, all with unique parameters. And then those different components are combined into cites. So the parameters that define a cite really tell you about which components are part of each cite. And again, you can have many different types of cites within a gas field simulation. So for example, you might have some sites that include unloading wells, and you have other sites with wells that maybe don't unload or unload at a different frequency. Once we have sites defined, we can combine the sites into a gas field. So parameters for a gas field are things like the number of each type of site that we defined at the lower level, as well as things that relate the sites to each other, like the distance between sites. So once we have the gas field data structure defined, we can then pass that into a simulation. So we don't have to pass each individual component directly into the simulation. We can combine them into one gas field object, and that's the thing that's actually passed to the simulation command. On the other side, we have leak detection and repair programs. These are not so many levels deep, but again, we have things like the detection function. That's the probability of detection curve I mentioned earlier. The sensitivity of the program and the survey frequency. So all these parameters are packaged into a leak detection repair object, and that object is then passed to the simulation. Finally, we have time settings. So we need to define the length of the simulation and the time resolution. And if you look at the details of how the code is written, those time settings also get passed to the leak detection program and to the gas field program. And that allows for a little bit of predefining variables that allows the code to run faster. So now I'm going to go through some example commands for each of these boxes. but keep in mind how they fit into the bigger picture of the data structure. So first I'll start with components. There's a reminder of where this fits into the tree on the right there. And the pictures are showing some examples of components you might want to run. You might want to model a valve or a connector, or you might be modeling a tank or a thief hatch, various things that can emit gas. So the few lines of code I'm showing are an example of how to define a component. I have the name of the component there. Emission data path points to a file that defines the distribution of emission sizes for that component. In general, Feast uses a bootstrapping method, so that file includes a long list of different emissions that were discovered in a set of studies. And this is actually the default file that Feast runs on. And so that default file is a compilation of 6 studies that all measured leaks at the component level and includes all types of emissions from well pads. So it includes pneumatic controller vents as well as fugitive emissions. I should clarify though, it actually doesn't, that data set doesn't include unloading. So if you want to include unloadings, that needs to be specified differently. The next variable there, emissions per comp. So that essentially defines the fraction of components that are emitting at the beginning of a simulation. So in this case, if we're figuring that there's around 600 components per well or something on this order, we're talking about a few emissions at each well. And then finally, we have an emission production rate. And that is defined in emissions per component per day. And if you look at, there is an example run script available within Feast, and the units are noted within that run script. I've taken them off here to keep the code compact, but just be comforted that if you're confused about what the units are, they're available in the run script, as well as in notes within the code itself.
Can you repeat what the units of that one were real quick?
Yeah, so they are emissions per component per day. So to unpack that a little bit, you can see I've written, instead of just the number, I've written like 5.4 divided by 650 divided by 365. So what that's coming from is, if I look at, for example, data from CDPHE, so from data from Colorado, and look at their OGI program, 5.4 is about the number of emissions they find per well per year with an annual OGI survey. So if we then divide that by about 650 components per well and 365 days per year, we can get an estimate of the number of new emissions that occur per component per day. So what I'm representing there is 5.4 new emissions per well per year, and then I've converted the units to be per component per day.
So that's kind of your generation rate of emission sources.
Exactly, yeah. Yep.
Chandler, one question I wanted to highlight from the chat that others might find useful. Techly asks if there's any data to support applicability of emissions distribution or probability of leak rate for a given equipment, example, pneumatic valves in upstream production sectors.
So your question was about the emission distribution.
Right.
Yeah. Yeah, so there is some data regarding this. So some studies do have specified the component type associated with each emission that they observe. Personally, I haven't separated that data out, but it's something I'm interested in doing, where we could say specify one component type that was tanks and a different component type that was open-ended lines, and each of those component types would have their own emission distribution. So yes, there is data available, but it's not included in Feast at this point. If it's something that would need to be specified as a custom setting.
Yeah, and this is where if you have access to your own data, whether it's your company's operations or whether it's data collected by the state as part of their methane regulations, it might be interesting to use that data to input to Feast and see how the performance of different technologies turn out.
Okay, so I'm going to move on to another example of a component object that we can define. But yeah, please do write a comment on the chat if you have questions, and I'll pause again in a few minutes. So the last example I gave was of fugitive emissions, but we can also specify vents, that is, emissions that aren't going to be repaired even if they're detected. So one way to do that is very similar to what I just showed. I'm even specifying the same emission size distribution in the data path there. But the one command that does need to change is this base repairable. So if you recall in the previous slide, there was no parameter called base repairable. And that's because by default, that's set to true. So by default, if you define a component in this way, any emissions that are detected by a leak detection and repair program will be repaired. However, if you do include that parameter and set it to false, then the emissions will be generated in the same way. But if they're detected by a leak detection and repair program, they won't be repaired. So a pneumatic controller is an example of that, but also emissions from tanks are sometimes vents and sometimes leaks, and so they're represented in, we can capture those two types of tank emissions by using these different, by defining two different component types with a different setting for whether or not the emissions are repairable. So I'll give one more example of how to define a component here. And this one is set up a little bit differently, just as an alternate way to define a component. I'm representing an unloading well here. And you'll see instead of specifying a path to an emission distribution, I'm instead setting this parameter called episodic emission sizes. And here I've just entered one value. It's in units of grams per second. But in principle, you can enter a long list there, and again, Feast will select emissions from that list with replacement using a bootstrapping method. You can also set, as an episodic emission, you can set the duration of those events as well as the frequency at which they occur. So that gives us 3 examples of components. Next, I'm going to move on to how to combine those components into sites and how to combine the sites into gas fields. But I'll pause again here to see if you've thought of any more questions about defining components. Okay. So once we have a bunch of components defined, we need to combine them into sites. So this is an example of how to do that. Here I'm defining a dict, and I'm calling in a couple of different types of components. So if you looked on the so I have comp dict equals, and then there's a fugitive component type, and I'm setting the number of those components equal to 300 times the number of wells in the site that I'm representing. And then I'm also setting this variable called parameters to a copy of the fugitive component object that I defined previously. So the takeaway here is when I'm setting up a dictionary of sites, I need to define the number of components of each type that are in the site, and then specify the object that contains all of the characteristics of that component. So I'm gonna move on. There's a similar process for gas fields, and then I'll pause for questions after I talk about the gas field a bit. So the gas field command here is pulling in 2 different objects. The first is the site dict that I just gave an example of on the previous slide. And it's also pulling in a time object, which I will define in a bit. So but the takeaway here is when you're defining a gas field, you need to include a dictionary of sites and a time object that defines things like the duration of the simulation and the time step size. So I'll pause again here to see if there's questions about how to combine components into sites or how to combine sites into a gas field.
Chandler, can you talk about the number of different types of sites you can define in the site section?
Yeah, so you can define as many sites as you want. Here I'm only here I'm defining one site. So on the first line there, you see that at the end I'm calling this site command, which creates an object which I'm referring to as basic pad. But in principle, you can define as many of those as you want, put them all into a dictionary, and then pass that dictionary into the gas field here.
So if you were to kind of set up a gas field, you could either define every single site as an independent dictionary, or create some basic site types. So say, a model of a site with 2 wells, and a model of a site with 3 wells, and a model of a site with 4 wells, and then add, 10 sites of likeness of the site of the 2 well style, and 20 sites that are 3 well sites or something like that. And each of those would have the same characteristics.
Exactly. Yeah, that's exactly right. Oh, I think Arvin was saying something. There we go.
Yeah, I have a question that's coming in. How does the model handle wet gas or mixed oil fields?
Yeah, good question. So feast does not track gas composition. So the only way you could, in principle, assign a different emission size distribution or a rate of new emissions occurring to represent different types of gas fields. But you cannot, feast does not track gas composition.
Yeah. And you can also define the number of components and type of components that are present in a wet gas field versus a dry gas field.
So would it, just thinking about a gas field, and maybe this is where the LDAR program comes into play and the time settings. But if I were to basically say, okay, in my gas field, there's a total of, 200,000 connectors and, or 100,000 flanges and whatever. Could I define just one big site with my total number of components? And how would that differ from defining many sites with the subset of components, or a subset of those at assigned to each site individually?
Yeah, so you could put them all in one site, and for technologies that are looking at the component level, they're not, so something like an OGI camera, feast doesn't model any influence between different components for that type of technology. However, if you're modeling something like a plane that's looking at site level emissions, then it would be very different, because the plane would the plane would see all the emissions from this one mega site that you've created as one giant emission.
So I was looking at Tekla's last question, and his follow-up on it was, on the chat, was on the wet gas or mixed oil fields, sites having potentially different equipment. So I think that would take the total opposite of the scenario that I just proposed, where you define each individual site as its own dictionary with its own leak or component types, right? So
That's right.
each site would then have its, be individually developed.
Yep, that's exactly right. Yep. And in the modeling, in practice, probably there's going to be some median that makes sense where we're not having to define too many different types of sites, but still capturing the important characteristics of the gas field. Okay, I'll move on for now, but yeah, please do keep posting the questions in the chat, and Arvin will make sure that they they get addressed. Okay, so if we want to define a leak detection and repair program, there's a similar process. Sorry, I need to move the way the screen is displayed here. So here I'm defining another dict, and I'm specifying the parameters that characterize the optical gas imaging camera. So first is the survey interval, and this is the units here are days between surveys. So 180 days is roughly half a year. The value I'm calling mu is the emission rate with a 50% probability of detection. So that characterizes the median of the probability of detection curve. And then the lambda value defines the width of that probability of detection curve. So the bigger lambda is, the broader range there is between detecting all emissions and not detecting any emissions of that size. And finally, the survey speed determines how long it takes to conduct a survey of the gas field. And that, for component-based technologies like an OGI camera, that's specified in components per day. So once I've set up that dict, I can define a technology detection object using this tech detect command. And I've taken out a few lines of code here to make it a bit more tractable, but essentially this star params is a dict of several different types of leak detection and repair programs. And the star format just means that it's going to read in each item in the dict separately. So the takeaway here is there's a command, tech detect, and you can pass in time parameters, the gas field, and the parameters of the leak detection and repair program that you want to represent. And it will create a leak detection and repair data object that can be passed into the simulation. So similarly, for a plane-based technology, we have the same data structure, but we have a few different parameters. So again, I have this survey interval, a mu value, a lam value, but instead of components per hour, I have sites per day, because again, this is a site-based technology. And then I also have a lam2 value and a mu2 value. So these refer to the follow-up survey that is component level and actually identifies which components may need to be repaired. And finally, I have secondary comps per hour, which defines the speed of the secondary survey. So moving on to defining a time object, I have two parameters I can pass into that. One is delta t, that's the time step size. Again, this is units of days, so 1/24 is 1 hour, 1/24 of a day. And the end time, also in units of days. Here I set 3 times 365 is 3 years. So finally, once I have all these different data objects defined, I can pass them into the field simulation command, and it will read the data from each data object and generate results. So now I will see if there's any more questions. So this is all the content I have explaining how to enter data into, or how to customize a simulation. And these commands are all available in the example run script, which is included in the Feast software and on the GitHub page. But if there's any questions about how to customize a simulation, now is the time.
So there's one question here from Sam. Is survey speed representative of a single site or the whole field?
So survey speed for, because I'm not sure exactly. So survey speed for a site-based technology is defined in terms of sites per day. And so, for example, if you were simulating a gas field with 100 sites and you could simulate 50 sites per day, then the duration of the survey would be 2 days. For a component-based technology, where say it's surveying 400 components per hour, if we have, say, a site with 600 components, it's going to take 1.5 hours to survey that site. And then if you take 100 sites, it's going to be 150 hours to survey all of those sites. And there is a, by default, Feast assumes that the component-based survey workers work 8 hours a day. And so that parameter can be adjusted as well. So the 150 hours to get at the number of days that the survey would last, you would need to divide by 8, because the assumption is that the survey work occurs over 8 hours per day.
Yeah, and just to add on to that, it really depends on the kind of data we have on new technologies. For example, for something like OGI, there's been a lot of experience using OGI for leak detection surveys. So we know roughly what the speed is. So it's 5 to 6 sites per day for average site sizes. If your sites are unusually big, you can reduce it to say 2 sites per day and whatever the corresponding components per hour are. But for new technologies, like say a drone or a truck-based system, there's not a lot of real field data available. And so we try to extrapolate based on what we know or based on some of the studies we have conducted ourselves. But you're absolutely right. Like as we gather more information and we get more data from some of the recent field studies, we'll have a better handle on what the survey speeds are. But in general, it's, if you ask a given technology to survey 1,000 wells, that's under my control. What is their average speed? That's what we put into Feast.
Great. All right. So
is there a resource we can look at to see the name of the different parameters and a description of what each parameter is? So for example, when we went over components, there was, the component name and emission data path and emission per comp and emission production rate. And then I'm assuming there's several others. So for instance, when Chandler put the example of event up, there was another parameter, this kind of repair, on detection parameter that was set to false for vents. Is there a one place or a piece of documentation that you could point us to that says a component has these potential input parameters or parameters that can be defined? This is what they default to, and this is a description of this parameter.
Yeah, so I'll show you what we have. So if we look at the GitHub page, in the read, oh, that's not the GitHub page. I'll bring back the GitHub page here. So to answer your question, Clay, the best way to look at every parameter, because is to go into the definition of the function that you're working on. So
right,
and each function lists all the parameters right at the top of that function, and they should generally have a note on units and the name should indicate what that parameter is used for. So here, for example, I'm looking at a tech detect object, and you can see all the units listed out and all the parameters and the type of parameters that are available. I think compiling all this into one document is something that maybe Arvind and I can work on getting out to you guys in the near future. But for now, the best way to do it is to look here.
Yeah, this looks documented well enough for us to, I think, look at that and understand those parameters.
Okay.
I think since this is kind of a development effort, I don't know that it pays to move everything to a documented version until we, have a releasable kind of, finalized or near finalized version.
Right. We do still want to keep this process light so that we can respond to your feedback or feedback from the technical working group. There are a couple of additional resources that we have to help you navigate the software here and find these files. First, I'll show a high-level map that I've included in the PowerPoint presentation here. So what I'm showing are the major directories in Feast and a brief description of the type of files you can find in each of those directories. So I don't know that I'm not going to read through all of this here today because I want this primarily to be a reference resource for you. But you can see that the parent directory is called feast_pte. That's the one that you'll download from GitHub. And it includes meta files, so things like the license and the README file, the Jupyter tutorial, and a template for data entry that I'll explain in a moment. And then within that directory, there's a subdirectory called Feast, and that contains all the modules used in simulations. And a module is Python speak for a file. And then within that Feast directory, we have a module called field simulation, and that's where the highest level function is stored. So that function is the one that you'll run to actually start the simulation. The detection modules directory includes all of the files that are used to define leak detection and repair programs. The general classes and functions directory includes definitions of all the classes that are used in Feast. So so a few examples of classes that I've defined for the software are components. There's a class called component. Cites are a different cites are a different class. A gas field is a class. A set of leaks is a class. So these type of data structures are all stored in the general classes and functions directory. And then finally, the input data directory includes not only the files that Feast uses directly, but also the raw data files that were used to generate the objects that Feast uses. And if you want more, so this is a high level map, and if you want more detail, you can look at the README file, which I'm showing now, and it lists every file that's in the software and shows you where to find them. So those are some additional resources to help you navigate the software and find the file that you need to check to see what parameters are available and what the units for those parameters are. And in addition, below that, I've included a brief description of each file. Right. And and finally, one related point here is the results files. So when Feast runs and generates a result file, it will store not only results of the simulation, like the time series of emissions and the cost of surveys, but also all the settings that were used to run the simulation. So when you, so at the bottom of the README file there's a description of how you can load a results file, as well as every one of the parameters that you can access within that results file. Okay, so at this point, I'm going to move on to looking at how to define your own custom emission distribution file. But before I do that, I want to ask if there's any more questions about how to enter data or customize the model, or how to find documentation of parameters. Okay. So I'm going to move on now and show how to define your custom emissions file, like I mentioned. But also, I remembered I have one more thing to show you from the tutorial as well. So I'll switch to that. So again, there's these examples of how to generate custom components. So that's basically what we just went through in the PowerPoint presentation. And then you can generate a customized result using those settings. And then there's also, I've also included an example run script in the software package. So you can look at that through the GitHub repository. But the Jupyter notebook also includes an example of running that file, and it takes a little while. It's going to run 30 realizations of the scenario that's defined there, and each realization is going to take tens of seconds on this server. And so once that's done, you can then load the results in a couple of different ways. The first way to look at the results is you can use this results analysis function that I've included in Feast. And that will go through, you pass in a directory to that command, and it will go through every results file in the directory, pull out a time series of emissions as well as costs and a list of the names of the detection technologies that are there. And once you have those arrays, you can use them to create a customized plot. And so here I've included an example of how to do that. Again, I'm not going to go through it. You can look at it on your own time. But I used this fairly long plotting command, and it looks long because I'm defining axis labels and font sizes and colors and all these different things. But it also shows you how to do that, but also shows you how to use results from a directory of realizations. And it generates the plot I showed in the PowerPoint at the beginning of the presentation with the time series of emissions on the left and a box plot of the distribution of emissions on the right. A second way to look at results from a set of realizations is to use one of the built-in plotting functions I've included in Feast. So this is the abatement cost plotter. So again, you pass in the path to the directory that you want the command to look at, and it will load all of the results files and generate a box plot of the distribution of mitigation costs for that file. So the takeaway here is that there's examples available in the Jupyter notebook that you can look at to understand how to interpret results. So I'll pause here again briefly before moving on finally to the example of how to create your own emission distribution file. Okay, so this is the last piece I'm going to have before putting up a slide with directions for installation. And this is how to define a custom emission distribution. So if you look inside Feast, I'm looking in the copy of the software that I have on my own computer. There's a file, an Excel file called raw data basic template. You can open up that file, and inside it has a few different parameters you can enter. It has a place where you can write custom notes. So I'll zoom in so you can see what I'm doing. I'm going to say webinar example file. You can also enter the number of wells in the study and the number of components per well. And Feast uses this to generate the number of emissions at the beginning of the simulation. So if you don't specify the number of emissions at the beginning of the simulation, then it will look at the number of wells you're simulating, or the number of sites, and the number of components that you're simulating, and then look at the number of emissions that were detected in this study and calculate the expected number of emissions for the beginning of the simulation. So for now, I'm just going to say 100 wells in the study and 600 components per well. Then down below, under the methane flux heading, you can enter all of the flux measurements from the study in units of grams per second. So I'll enter a few here: 0.13, 0.5, 6. Oops, that needs to be a 6. And then I'll save this file. I'm just going to save it to my desktop for now. And I'm going to say webinar example save. So now I have this data entered in a standardized format, but there's one more step before actually using it in a feast simulation. And that is converting this Excel file into a data object that feast can interpret. So in order to do that, I need to open up a command prompt. I'm going to use an Anaconda prompt here. And I need to move to the directory that I've just saved this file in. So I saved it to my desktop. We can check and make sure that that file is there. There it is, webinar example.xlsx. And then I need to enter a Python command. And this command is going to say, first, I'm going to say Python so that the computer knows it should look in, that it should run this module as a Python command. And actually, before I do that, I need to activate the environment that I want to work in. So I need to go Honda, act feast-dev. So now I'm in the environment that already has feast installed and any necessary packages. And now I'll run the command. So Python tells the computer it's going to be a Python command. Then I need the path to the script that will process the template file. So this is feast_pte. I've forgotten what the name of the file is, so I need to check. So I will go list the files in this directory, and I'll be able to see it then. So it's called template processor.py. So then I can enter that file here, template processor.py. And then I need to give the next item is the path to the template file that I just defined. So that's that's webinar _example.xlsx. And then finally, I need to give a path to the output file I want to generate. So I'm going to say webinar example out.p. So I run this command. And I need the full path to the template file. So this is feast_pte / So it takes a moment to read the Excel file, and then it should generate an output file. So it comes back with this message: successfully created emission size distribution object. And if I look in my desktop here, I can see there's now a file called webinar example out.p. So if I wanted to use that file, I would enter that path into the emission distribution parameter when I define a new component. So again, you can find the template file within the software package when you first download it. It's in the package that will be downloaded when you download Feast. I actually don't see it here at the moment, but if it's not there, I'll make sure I put it up there right away. And you can look at the template processor file here as well. And so if you look in the comments here, it tells you what the parameters are that you can pass into the Python command. So with that, I'm going to bring up the installation instructions, and I'll leave them on the screen here, and welcome any questions about the template processor, or at this point, anything else that we've talked about today.
All right. Thanks, Chandler. I have one question. So when you explain the template, so just as an information to everyone on the webinar, the last portion, the template processor and adding your own emissions, is only required if you want to add in your own custom emissions distribution file or distribution data. But if you just want to run Feast with the default distribution data, you don't have to do the last part. So a question related to that. So let's say I have 3 different emissions distribution, one for leaks, one for vents, and one for something else. So do I have to create 3 different Excel files and then process them, or can it all be done in just one Excel file?
Yeah, so you need to create a separate Excel file for each new emission distribution that you want to create. So in the example that Arvind just gave, where you have a distribution for vents and a distribution for leaks, you would need different Excel files to accommodate those.
All right. I think the formal portion of the webinar is over. So it's open for questions on anything that you've heard in the past hour and 15 minutes. I will send a follow-up email to everyone in the next couple of days that will have the link to the GitHub page, link to the website with more information on Feast. We'll upload this webinar, so it'll also be available online. And someone asked for these slides. These slides will also be uploaded. Here, there's a help email called feast.help@gmail.com. I mean, of course, people in this webinar, you can directly email Chandler or myself or for questions. The help email is exclusively for when we make Feast publicly available, and there might be questions from the public who are not on this webinar. But if you have any pressing questions, you can send either of us an email on Feast. Clay, did you want to say something?
No, I didn't mean to mute or unmute. If I did on accident, I'm trying to follow the Feast install instructions here.
Oh, okay.
So Chandler, these install instructions will basically install Feast in your Python install or your or your Conda environment.
Yeah, exactly. Right. Yeah, so if you haven't worked with Anaconda before, first of all, you don't necessarily need to do that to run Feast. You can run Feast using any Python. I guess any way that you can run Python, you can run Feast. But right. I find Conda to be a pretty convenient way to do that. And so in the section of the instructions there that says create a new virtual environment to work in and activate it, that can be useful to ensure that we're all using exactly the same versions of the packages. And so it creates sort of a separate instance of Python on your machine that only has access to the packages that we explicitly install there. Whereas, like in my case, in my base installation of Python, I'm constantly installing new packages and it's a fairly messy environment. But if I want to make sure we're all getting the same have the same packages installed and are referring to the same versions, so we don't get surprising bugs. Having a customized environment can be helpful. And so once you run those commands, the conda create and the conda activate commands, then from then on, you'll be working in that specific environment. And then of course, if you want to use feast later on, you have to remember to activate that environment. I almost did it today during the webinar where I go to run feast and I'm not in the right environment and it's not installed. So that's something to remember later and not be surprised about if you get an error message.
So I'm also just kind of getting used to running stuff on GitHub and the like, and in PyCharm, to look at the actual Python scripts and play around and stuff. But would you recommend that I do that in PyCharm, or kind of I open them up separately in Jupyter Notebook or something else? Is there a,
Yeah, that's a good
to
question.
actually run that stuff?
Yeah, so I work in PyCharm usually as well. I find that to be a pretty, I like the way it's laid out. So yeah, once I have feast installed on my machine, I would then go ahead and open it up in PyCharm. I can switch to that. I would switch to PyCharm, but I'll switch to PyCharm briefly and then I'll bring these instructions back up. I think I even have it open here. So this is what PyCharm looks like if you haven't used it before. And I can look at all the files that are included in the software package on the left there. And if I open a file, like for example, right now I've got the example run script open. It gives some nice coloring to the to the script, so you can see the comments across the top in green, and then later comments that are just inline comments in gray, and different types of variables are given different colors. So I like to look at the software in PyCharm. I think it's a good solution. And you can also, you can set up environments where it will run different scripts automatically for you if you want to. So yeah, I think it's a good resource. And if you haven't worked with GitHub before, it's a resource that stores software packages I'd say that's its most basic function. But it also allows me to push updates to those packages periodically, and it will track and it will store my notes on what changes I've made. And then it also allows anybody that's cloned the package onto their local machine, you can then download those updates with a simple command. So if we're down the road, if it comes to that, you can email me if you need some help making sure you can update the packages. But GitHub is a good resource for storing software and providing a convenient solution for updating it.
All right, excellent. So I don't want to hold people on for much longer. Chandler and I will be here for like 5 more minutes. But if you don't have any questions, you're welcome to leave the webinar. But thank you all for attending the webinar, and please send us questions if you have any on this, and I will send a follow-up email in the next day or two with all the materials that you saw here today. But if you don't have any further questions, you're more than welcome to leave the webinar now. Thanks.
Hi guys, this is Arsina from Chevron. So first, thank you so much for this webinar and introduction. I don't have a question, I just wanted to share something from our side. Chevron has this lengthy process of giving permission for downloading specific things on your computer. And since I joined this project about 2 weeks ago, I've made the requests for those downloads, but this may take some time. So I in the beginning asking for your patience as I actually start to download stuff, then I'll have questions that will maybe behind what things are. So that, and also thanks for recording this. It'll be really helpful.
No problem. Thanks.
Yeah, thanks for the heads up.